Another medium problem from HackerRank. This one is called Kindergarten Adventures. Per my usual format, I'll look at the question, give you some time to do it on your own, and then go over my solution. So here we have Mira teaches a class of N students, and every day in her classroom is an adventure. Today is drawing day. The students are sitting around a round table, and they are numbered from 1 to N clockwise. This means that students are numbered 1. Yeah, okay, that's what I just said. And students 1 and N are sitting next to each other. So it's like if you have a list that's something that's like a straight in order thing, there's a connection between the last and the first because it loops around. After letting the students draw for a certain period of time, Mira starts collecting their work to ensure she has time to review all the drawings before the end of the day. However, some of her students aren't finished drawing. Each student in a list has a few extra minutes to complete their drawing. Mira collects the drawings sequentially in the clockwise direction, starting with student with ID X. It takes her exactly 1 minute to review each drawing. This means that student X, the one that she'll start off with, gets 0 extra minutes to complete their drawing, whereas the next student gets 1 extra minute, and the student after that gets 2 extra minutes, and so it's a cumulative thing. Note that Mira will still spend 1 minute for each student, even if the drawing isn't ready. So that's something to note. So given the values in that list of student times, help Mira choose the best possible X to start collecting drawings from, such that the number of students able to complete their drawings is maximal. Then print X on the line, basically. So we need to basically build a function that will take in this list of student times to complete their drawing, and spit out the index plus 1, not exactly the index, but just one more, because it's the student number, which is on a 1 to N scale. That's what we're looking for. And that is basically it. So I do have kind of an example here, so I kind of want to show that. Okay, so here's a quick example of what you can kind of think of this situation as looking for. So you're given an array on the right here, where we have the students in index 0 to 4. So this is 5 students total, and the first student will take 2 minutes to complete their drawing. Student number on the second student is or I should say student at seat 1, index 1, will take 5 minutes to complete their drawing. We see that this fourth student here is actually already done. So they have 0 for their number. And we're also told in the problem that T can be between 0 and N. So a student can be done or take a really long time, basically. So that's our maximum. Okay, so and here's kind of we're given an array, and I just want to remember that they're sitting at a round table, so the first and last student are next to each other. So even though the index is like 0 or 4, we should know that the 4 will loop around to the 0, and this should be considered a continuous thing. Okay, so that is the setup. So I'll give you some time to do it on your own, and we'll check out my solution afterwards. Okay, so to be completely honest, I think this is a mislabeled problem. I feel like it's not quite medium. I think it's more in the hard. It should be in the hard section. But anyway, I'm going to showcase my kind of brute force solution first, which wasn't very good, and then kind of show you like some of the patterns that I started to notice and how we can use that for coming to a better solution. So here we go. So the first thing to note is you can kind of just look at each student and assume that they're the one that you start with, and then just move forward through the list and just subtract 1 from each student's number, and just make a count, basically. So that's exactly what I'm doing here. So for example, if we start with the first student in index 0, 2, that student is not going to be done because they have a 2. So we can like tally. We're just keeping a running count of how many students are done. Here we're not done, right? Student at position 5, the next student will take 4 minutes. We can tally 1 down, and so you can kind of notice that we're actually subtracting the index, which is kind of interesting. So 5 minus 1 is 4 because that's 1 minute more that they're given, and so 4 he's not done. So that's still no one's done there. 3 minus 2, and this is 2 minutes in, that's a 1. You're not done. This person was done to begin with, so that's definitely a 1 there. And then this person at the 4th position, or at the 5th position, would have taken 1 minute, but they were done, a while ago already at this point. So this person will also be done at that time. So we have 2 people who are done if we started with 0 as our index. So here I have kind of a running total of everything, and I want to kind of explain a little bit here. So if we have a starting index, what I just did up above is what I'm doing here in this one row. So this whole row here is 2, 4, 1, 0, 0. The total number of students who are finished are 2. You can do the same thing with the first, assuming that you start with the index 1, which is the student with 5 minutes. Then you can just do the count there, and you can do that for each row, basically, each index. And get to a sum of total students finished, and we'd see here that this student, or this is the best answer, basically. This has the maximum number of students finished, so we would say we would start at index 3, which is student number 4. So that's one way of doing it. You can see here that the time complexity, though, is pretty large because we're going through each n element n times. And one thing I wanted to show you here, and that was not passing all the tests. So one thing I'll show you here is we can kind of extrapolate this into its own kind of like mini list, where we have counts of finished students by index. So if we start with the 0 index, we have 2 students finished. If we start with the 1 index, 3 students, and we saw that our answer here was this one, right? So that one had the highest number, so that'd be where we start. So that's one way of doing it. You can also look at it in terms of students who are not finished, because that's just n minus that number. So this is another way of saying the same thing, just flipping the coin, basically. So we're doing counts of unfinished students by index, in which case we'd still pick this one, but instead of the max number, we're looking for the minimum number. That's the same concept, though. And this is what we're going to be kind of like looking at. This the counts of unfinished students, because here we're going to start noticing some patterns, and I kind of was trying to do that with these colors before. So these colors match up with the numbers from up here. So if you were to start with number 2 in 0, then it would be the second student if you started with position 4. But it's going to be -1 because it's 1 minute past, right? And then the same thing with position 3 and 2 and 1. And so it kind of like has this like little diagonal, this diagonal situation going on here. And what you'll start noticing is, and it makes some intuitive sense, that there's kind of like a range in which these numbers start contributing to the total, but in the end they're not going to be there forever, right? Except for only one situation. So one thing to note here is that the student who was starting at 0, I'll say this student here, they never contribute anything to the total. Or should I say they, another way of saying that is if you look at the total students who finished, they don't really add anything, because the maximum will still be the maximum with or without them, since they're adding 1 to every single outcome. The same thing is basically true for the student who has 5, or the max being the total number of students. A student who has n minutes to complete will never be done. So we see that here and here and here. So a student with the maximum number doesn't matter because they're never adding to the total. And the student with 0 will also be in a similar boat. They're basically contributing to the total in a consistent way. Every outcome will be included, will have their contribution included. So effectively they don't matter. So we can actually just ignore any student that has the max or the minimum of minutes. So let's actually check out how these students contribute to that total. And the total I'm talking about is this unfinished one here. Let's see how each student contributes to this unfinished students table here. And we'll start with the student at the third student, which is at the second index, with 3 minutes left to do their drawing. So what we should notice here is that when we pick them to begin with, they're not going to be done, and they're not going to be done because they're not 0. So we know that if we pick that, that's one student who's unfinished. We should also recognize that if we go back 1, they're still not going to be finished because they have a 3 minutes, right? So we basically need to go back 3 in order to really account for all the times that student is not finished. All other times, though, the student is going to be finished. So here's what it looks like. So we start at position 2. We consider that as a 1 because the student's not finished at that point. Then we can go back 1, also not finished, and go back 1 more, also not finished. So the thing to note here is that each student has an interval of indices in which they are unfinished. And we're going to need to I want you to keep that interval idea in mind, that each number is actually kind of like 2 numbers that represent the interval at which that student is unfinished. So we can add in then another student, like the one at position 2, or sorry, position 0, who has 2 minutes. So we will add 1 to the 0 position, and then we have to go back 1. But remember that going back 1 means that we're going on the 4, and the 4 will add 1 to that as well. And that's the 2. That's representing 2 minutes. Okay, so the next student is the 1, and they're done right away, basically, but the only time that they're not done is when you are starting with them. So on 4, we need to add 1 to just the 4. And then we can add in this student who has 5. I'm going to ignore the student with 0 because we know that they don't contribute anything. They're already finished, so they won't be contributing to the unfinished students. So that's what my little note here is saying. So let's say the student with 5, we know that they're not going to be done. They're never done. So they're actually contributing 1 to every position. So we're just going to increment each one by 1, basically. And we get a final total here of 3, 2, 2, 1, 3. And if you remember, this is exactly the same thing as what we have up here, 3, 2, 2, 1, 3. So this idea of taking these intervals is exactly the same thing that we saw before. And we can come to the exact same conclusion, that the starting at student number 4, or index 3, is best. I've added the student with 5, and we saw that the best student is at index 3. But did we even need to add that student? Because they're just adding nothing, basically, because the max is still the max. If you add 1 to everything, it's still going to be the same. Or sorry, if the min is still the same as the min from before. So in this situation, if I completely ignore students that have the max, then I am left with the same answer, the same result. Instead of a 1, I see a 0 instead, but that's still the minimum. That doesn't change anything. So I'm actually going to ignore students with 5 or 0 because they don't contribute anything to the total. The clincher here is how to make this more efficient. So right now you could create a loop that's looking at the start and end of the interval and add to a list or an array and like increment from that start to the end 1. That could be something. That is not much more different than the original issue from before, where we're looking at basically n times n, and you're not doing anything more efficient here. What you can do to make things more efficient is to use intervals and a running sum. So here I'll look at student in the second position again, number 3, and I want us to recall, like, how did we get to the interval? How do you determine what the interval is? So the thing to note is the student at index 2 has 3 minutes, so we need to go backwards and figure out the starting index. We should recognize that each student's interval starts as their index minus how long it takes them. But we need to add 1 just for the accounting to make sense. So for example, with this student in position 2, so that's a 2 index, we have to subtract 3 from that. And if we do that, we'll get -1, which is, we know from what we just saw, that's not quite right. It's actually going too far back. So you just add 1 on top of that. That gives us index 0. So we go from 0 to start, and the ending interval is simply 1 more than the student's current index. Index 2 is the last point in which the 1 shows up. After that, it is guaranteed to be a 0. Why is it guaranteed? Why is it guaranteed to be 0? Because by the time you get all the way around, as long as you're not a student with 5 or like the max number, you're guaranteed to be done by that point. That is how we got those intervals, but here is how we make things more efficient. We can use a way of representing an interval by using a running sum. So what I mean by that is, let's take our start of our interval, which is 0, and add 1 to that. So start, add 1. And in the end, which is the 3, 1 more than the index, we add a -1. These are constant time, and we don't need to do anything at this point. We could just say +1 here and -1 at this point. There's nothing in the middle. We're going to keep track of a running sum. And so you can actually convert the thing on the right here, which is like this abstracted running counts, which is using this like interval representation, and then do a running sum. So what I mean by that is you just loop from the beginning to the end, and you just keep a running sum of what's going on. That would be a 1 plus 0, so that's still a 1. That's what we see here. Then we add a 0 on top of that. That's another 1. And then we see the -1, which we add, and we get a 0. And another 0. So that's how you can actually keep track of a bunch of intervals without having to loop between the two. So let's check out the code. So here in my solution, I have two functions: a little helper function called sanitizeIndex, and the actual solve function. So I'll just quickly go over this sanitizeIndex idea. Because we're dealing with this list that is kind of looping around, it's possible that we'll calculate a negative number for an index, but we should know that that negative number isn't quite a negative number, that it is properly looping around. So this sanitizeIndex is just taking the index that we're calculating and spitting out the proper index. If it's basically too far to the left or too far to the right, it like puts it back on the right scale. So it's given an index, like a raw index, and then an n, which is the size of the array or list. And if the index is already valid, then it just kind of spits back the index because it's already within the right range. If it's a negative number, then we know that it's we're trying to loop back to the end of the list, and so we just do n plus that basically, and that'll properly give you a number. So for example, if I have -1 in that situation from before with a length of 5, then I know -1 plus 5 is 4, which is the last index, which is what that represents. If the index is out of range, then we can just do a little modulus trickery and just divide out the whole index, and you get the proper number. Which is to say that if you're at index 5, for example, then you're like 1 more than the 4, which means that you're supposed to be on 0, which is 5 divided by 5, basically. It's a 0. So that's what that means. Okay, so here is the idea. So at first, I'm grabbing the length of the list coming in, the number of students, basically. So I can say this is n as number of students. And here I'm going to have this running sum builder. So if I go back a second, this is going to be this thing here. It's going to be like an empty list where each index represents this like interval representation. And that's what we're going to keep track of. I'll start everything with 0 though. And here I will enumerate. So I have the index and the value at each student, for each student. And here I'm looping through it big O of n time. This is big O of n basically. So this is fairly efficient in that regard. And basically if not value, so if the value is 0, that's the only situation that this comes up. So if the value is 0 or the value is equal to n, that's the situation where we have a student who can never finish. So for those, I'm ignoring them. I'm just continuing. Otherwise, I will look at the index start and index stop. We remember that index start is just the actual index of the student minus their value plus 1. And that's what I have here. And then I'm sanitizing that index using that sanitizing function. Just in case I go too far left or right, I don't want to have that issue. So that's why I'm doing that there. For the stopping, I'm just taking the current index plus 1, because we know that if you go 1 ahead, it's going to the student will guaranteed be finished by that point. Okay, so there's one small caveat here, and it's the fact that because we're doing this running count thing, we need to keep track of any situation where the interval spans that the cutoff gap, which is between 0 and the last number. So if you have something that spans that, then it will not be properly captured by starting the running sum at 0, because the way this running sum thing works is we need to start with a number, right? So the starting number needs to capture everything that's happening at that point. So that's why this is happening here. So this is a small caveat with this kind of simplification of having a list represent something that's circular. Other than that, we have the running sum builder at the start. We're going to add 1 when it starts and subtract 1 when it ends. And that's basically that's what that simplification is. These are constant times, so this is pretty quick. At that point, we are looping through each student and getting all their intervals. And now we need to do the running sum. So here's where the magic basically happens. We'll have a min counter. And again, min because we're minimizing the number of students who are not finished. And I'm starting it with infinity because every number is smaller than infinity. And here is the best starting index that we're going to keep track of. Whenever we find something smaller, we're going to keep track of that. That is effectively our answer. And here's the running sum, which I'm initiating with 0. And all I'm doing is looping through that sum builder, the running sum builder, which has a bunch of intervals that are abstracted with +1 or -1 here and there. And I'm enumerating, so I'm getting the index and the value from that. And the index is basically the starting index. That's what that represents. So here, this index here represents if we were to start at that point, how many students would be unfinished at that point. And so all we do is we take the running sum and then we add that value to it, which is our running sum. And then we say, okay, running sum, are you less now than the min counter? If so, we reset our min counter and we set our best starting index as the starting index that we're currently at. And one caveat here is that we need to give the smallest index, the smallest student, that number for the student. And this logic will ensure that because we're specifically saying if you are less than the min. If it wanted the greatest number, then we'd say less than or equal to. And in the end, we return that index. But remember, we're adding 1 to that because we're not using 0 indexing for the student number. It's 1 to n. And so that's our answer. So let's check out our code, run it. Looks good. And let's run it against the submission. All right, we did it, folks. It looks good to me. Let's check out some big O notation and time complexity. So we did run through the entire list once. Then we went through the running sum builder, which is just another list of n length. So this is also big O of n. But it doesn't go further than that. So total time complexity, big O of n on that. So fairly efficient. So thank you folks for tuning in. If you find this kind of content useful, please make sure to like, subscribe, and do all the good things. And I will see you next time. Take care.